What's really critical here is where do we get the A coefficients from? Because this whole theory and mathematical exercise I've just gone through would be of very little interest if you had to come up with values for A1, A2, and A3 by hand. It'd be, very, very awkward, even though there are many, many shapes you could come up with. But the wonderful thing about, and this was part of the conscious design, was to make this random variable x linear in these A coefficients. Because suppose you have 3 quantiles, maybe you've assessed these from an expert, maybe these come from your data, but you've got your 10, 50, and you've got your 90 points, for example, on your cumulative distribution. You've got that from, could be, as I say, assessed from an expert, could come from empirical data, could come from anywhere. But if you have those points and you want a probability distribution at a minimum that goes through all 3 of those points so that it can represent your data well, then what you actually have there is three linear equations and 3 unknowns, because you have, you've got y1, y2, 0.5, y3, 0.9, and you've got 3 equations and 3 unknowns, and they're linear in these A coefficients. But we know a lot about the solution to linear equations. It's very simple. There it is. It's done in closed form all the time. And now, from these 3 points, 10, 50, 90, of 40, 50, and 70, those are the 3 points, you end up with these A coefficients in closed form by inverting this little matrix Y and multiplying it by your X values. And that's all there is to it. All right. So that's if you have 3 points. Now, what if you have a lot of points? In practice, we might have lots and lots of data points. We might have hundreds of data points or thousands, right? And you would like, in principle, to be able to come up with, let's say, in this case, a 3-term metalog or a 4-term metalog that goes, you don't want it to go through every one of those points because you know that there's a lot of noise in the data, but you'd like it to at least reasonably go through the middle of them, okay? And what do you mean by the middle? Well, this equation I just showed you generalizes to ordinary least squares, which is the same as multiple linear regression. You can see this is basically a multiple linear regression equation in these coefficients, A1, A2, A3. In the literature, you might see beta 1, beta 2, beta 3 as your regression coefficients. But anyway, with this simple closed form equation, you can come up with the coefficients of the metalog that will go in a least squares sense through whatever set of data you've got. So there we are. And that's the basic way you get metalogs from data. That's why we say metalogs are parameterized by data. You can think of these data as parameterizing your metalog, and the metalog reflects, therefore, the shape of the data. Now you can do, I've done a 3-term example here, but you can do this with any number of terms. And the more terms you get, the more you will find that the metalog will modify itself to more closely fit the nuances of the shape of your data. And we'll go through many examples of this as we go forward. So now there's another feature of this. If you might say, well, what's the relationship of this to maximum likelihood, which is how people ordinarily, particularly statisticians, ordinarily fit probably the parameters of distributions to data. Well, it turns out this ordinary least squares is the maximum likelihood solution if you make the standard Gaussian noise assumption. So you don't even have to worry about that either. You've got the maximum likelihood representation as well.